All right, so 1.23. Okay, so here we have a joint density function, f of x comma y equals xy when x is between 0 and 1, and when y is between 0 and 2, and 0 otherwise. So the first thing they ask is, are x and y independent? Well, what do you guys think? How do you show that two random variables are independent? Does anybody remember? Multiply the marginal densities to see if equals a joint. Yeah. So then what would be, so basically we can kind of already answer A, but let's do B and C then. So then let's do B and C. What is B? I want to find the marginal density function of X. So I want to find f of X. So how would we get that? We would have to integrate negative infinity to infinity of our joint. And we want to integrate with respect to y. So we clear all the y's. We add up all the y's together. And so then we have xy. And y goes from 0 to 2. This is dy. So we're integrating with respect to y. So x is treated as a constant, and we get x y squared over 2, evaluated from 0 to 2. So when we do that, we get 2x. So the marginal density function of x is equal to 2x. And that's when x is between 0 and 1, right? So let me just make sure that the bounds are correct. Yeah. Okay, and so then what about f of y? F of y, the integral from negative infinity to infinity of f of x y dx. And dx goes from 0 to 1 of xy dx. And so I get x squared y over 2 this time from 0 to 1. And when I plug that in, I get y over 2. Right? So then the joint density is y over 2, or half y. And so then the question for part A asks, are x and y independent? In other words, is f of x comma y, is that equal to f of x multiplied by f of y? And obviously it is, right? Because this is xy, and f of x is what? Just 2x. And then f of y is what? Y over 2. When you multiply it, you get xy. So yes, they are independent. Okay. Can you talk a bit about when one range is in terms of the other, like negative x? Yeah. So whenever that happens, like I've mentioned before, it's better to actually draw out the region. So whenever you have something like negative x less than y less than x, right? I want to graph it out. I want to graph it. That's the best way I can explain it because it can get quite confusing if you try to understand it purely from an algebraic point of view, just by looking at the um, inequality. So when y is less than x and it's greater than this, right? You would have a rectangular region that looks like this. So as x changes, so does your y. But I have a better understanding of it because I understand what the region looks like. So as x changes, so as my x values change, my y's have a certain range that it can range in between. And usually you see this in like conditional probability. Um, and the idea is that the the probability density function that you get has to add up to 1. So sometimes these regions, these bounds are necessary. So if you're integrating for y, what would the bounds be? Negative x to x. If you're integrating for y, yeah. If you're integrating with respect to y, then the bounds would be from negative x to x. Mhm. Okay. So far so good. Just wanna so okay. All right. So then these are again these are probability density functions for x and y, marginal densities, right? And so this x here is between 0 and 1, right? So x is between 0 and 1 here, and then y is between 0 and 2. Okay, so now part C. Part C asks, no, we already did part C. Pardon me, this is part C. Part D asks, find the expected value of y. So how would we do this? How do we compute the expected value of y? Multiply y by the marginal of y. Yeah, so you're going to do exactly what you're supposed to do by definition. This goes from negative infinity to infinity dy, right? We're dealing with the y random variable, and we found the marginal density for that random variable. So now we apply the definition, and again, this is important to understand that y goes between 0 and 2. So the integration bounds is 0 to 2. This is y times y over 2 dy. I can place the 1/2 in front. So this is 0 to 2 of y squared dy. So this equals 1/2 y cubed over 3 from 0 to 2. So I get 1/2 times 2 cubed over 3, which equals, you can cancel out the 2 here. So you get 2 squared on the top, which is 4/4. So the answer is 4/3. Yeah. Okay. And now the last one. What's the last one? Last one says, find a probability that x plus y is less than 1. That's E. So does anybody know how to approach this one? How do we approach part E? Find the area under the curve less than 1. So remember, this statement here is like a region. It's like a region in the xy plane. So I want to find the integral of over that region that we have to see of the marginal density function dx dy. And so that's why it's important to see what the region is. And the region here is a simple one because my x values go from 0 to 1, right? 0 to 1. And my y values go from 0 to 2. So my region is simply a rectangular region. This is my region, right? Of where f of x is defined. So this is region where fxy is defined, correct? And then when we graph f of x comma y equals xy, you would have a graph that you can visualize. But for now, we only care about the xy plane. That's all we care about. Now, the region that we're integrating over is this region, x plus y less than 1. So then how do we interpret this? Well, this region, you can write this as y is less than 1 minus x. So you can draw the graph. So this is 1, right? Of course, not drawn to scale. This is a y-intercept of -1. Your slope is negative. Your y-intercept is +1. Your slope is -1. So I have a line that goes like this. So if I just eliminate this here, and I draw a line, this line right here. This line right here is y equals 1 minus x, but I only care about the y being less than 1 minus x. So the region I really care about is this one. Do you see that? So then now, do you guys know how to integrate? What would be our integration bound? So here we would have xy. This is dx. This is dy. Now, what would be our integration bounds? It's really up to the way you dice the region. So if you dice it vertically, you would have one way of integrating. If you dice it horizontally, you have another way. So either way, actually, it's okay. It's actually the same, but just symmetric. But how would you do it if I were to cut this vertically this way? What would be the way how do we be integrating this? X and 1 minus x. So definitely there's going to be a 1 minus x, right? So if I were to cut it in this fashion, I'm saying that my y values are in my my y values are in between certain x values, right? My y values are in between certain values. So here, my y value is between 0 and 1 minus x. Right, that's right, Alexandra. So I would have to switch this guy around here. This would be the y first. The inside function, the inside integral will be with respect to y, and the outer with respect to x. And so then if I cut a slither of this, the y values of this slither, right, range between 0 and 1 minus x. This is with respect to y, my y values. For every x that I go over, the y values go from 0 to 1 minus x. Do you guys see why we have to do that? Because, so this is kind of like, this is sort of like a for loop, an iterated for loop, right? You have two for loops, one nested in the other. So your x values, like you're going through every x value, and for every x value, your y value ranges from 0 to 1 minus x. Do you guys see that? So like as I move across the x, the y's range between 0 and whatever that 1 minus x would be. And as you progress with the x's, the range of the y's gets smaller and smaller because x gets bigger and bigger. So do you see why we have to do that? And you see how we can also do the same exact thing in the other perspective. When we look at it from this perspective, it's the same idea. Because of the bounds 0, 1 are symmetric, it's going to be the same idea. It's just that this would be 1 minus y, this would be dx, and this would be dy. It's the same integral. Okay, and so now from here, we can just integrate. We can treat this x inside the inner integral as a constant. So this becomes 0, 1. This is x, and this is from 0 to 1 minus x, y, dy, dx. So then when you integrate this, you get y squared over 2 from 0 to 1 minus x. This is x, this is dx. So then you get 1 minus x squared over 2 multiplied by x from 0 to 1 dx. And you can take out the 1/2. 0 to 1. This is x. This is 1 minus 2x plus x squared dx. This is 1/2. And then you get the integral from x minus 2x squared plus x cubed dx from 0 to 1. And then you just integrate. So you get x squared over 2 minus 2x cubed over 3 plus x to the 4th over 4. This goes from 0 to 1. You plug in the 1, you get 1/2 minus 2/3 plus a 4th. And then when you plug in 0, you get all zeros. So here we just have a sum and subtraction of fractions. So then this becomes 6 over 12 minus, this is 4, 8 over 12 plus 3 over 12. So we get 1 over half. 6 minus 8 is -2 plus 3 is +1. So this is 1/12. And this is 1 over 24. Okay, so at this point, it just becomes a calculus problem from an original probability problem. Okay, is this understood? Any questions?
I have a quick question.
Yeah.
Looking at 1.2, number 1, A problem that I was having with the homework when dealing with infinity as a bound, um, I would often, I would just have issues with obviously the computation and dealing with infinity. Sometimes it would come out to zero, sometimes, it would be undefined because I was just doing the calculation, poorly. But do you think maybe we can do one with infinity as a bound, just to go over that?
So
Like
number one,
yeah, like maybe we can do the density function of like part C, 1.2 number one part C, or maybe whatever else you would think would,
part C.
yeah, would show that.
Okay. Um, so to do part C though, we have to do part A first. So let me take. Okay, so we have a density function x and y, and it's given by this formula, this piecewise function. And so we get that region again, right? We get that strange region where x is, or this time x is between y. So we get something like this. So here, this is y equals x. And here, this is y equals negative x. And so my region that the joint distribution is defined in, the density function, is within this region here, right? Shade that. This is the region, and this goes on forever because y goes on to infinity. Okay. And so now to find a little bit more information about this density function, there's this constant here that I have to figure out. So part A says find C. And how do we find C? We have to integrate the entire thing, right? Over the entire region. So let's call this R, right? So we had integrate across this entire region of the joint density. So then, and this has to equal 1 because this is a joint density, a probability density function. So by definition, it must, the integral of this over the entire region should equal 1. And the y's go from 0 to infinity. The x's, however, go between negative y to y. So we can also integrate this. So we're right now, these bounds are representing an integration where you're cutting this in this fashion. So you're saying for every y that you go up, the x's are ranged or are in between negative y and y. That's what you're saying. So that's why you're cutting it. You're cutting the region R in these kind of horizontal slices. You can also do it vertically. It's just that when you do it vertically, you're gonna create two different double integrals because so you would say that for every x, so the x's go from negative infinity to 0, but the y's go from negative x to infinity. And then you say the integral goes from 0 to infinity for the x's, but then the y's go from x to positive infinity. So that's why you have to split this into two different integrals. But we're not doing that. We'll be splitting it up in this fashion. So it's just one double integral. So then we get c x minus y, pardon me, y minus x e to the negative y. And then this will be dx dy. This has to equal 1. So I can take out the c, and this becomes c goes from 0 to infinity. The integral from negative y to y of y minus x e to the negative y dx dy equals 1. So step by step, right? So I'm going to look at this inner integral first. So I'm going to call this 1. So I'm going to put 1 here. And I'm going to integrate from negative y to y of y minus x e to negative y dx. Negative y to y, this is y e to the negative. So you can take out the negative y, right? Because e to the negative y, because this is with respect, this integral is with respect to x. So e to the negative y can be placed in front actually, and you get y minus x dx. So you can place this e to negative y on the outside here. And then you integrate with respect to x, so you get xy minus x squared over 2 from negative y to y. And then when you plug in the y, you get y squared minus y squared over 2 minus negative y squared minus y squared over 2. Let me just see. Okay, and then just want to make sure everything's okay. So y squared minus y squared over 2 plus y squared plus y squared over 2. So these cancel, and I'm left with y squared, 2y squared, right? And so then the inner integral here, 1 becomes e to the negative y times 2y squared. That's the inner integral. That's what 1 is. So now I can replace that inside, and I get c from 0 to infinity of 2y squared e to the negative y dx equals 1. You take the 2 out and you get 2c from 0 to infinity of y squared e to the negative y d. Wait a minute. Yeah, it's dy, right? Why did I write dx? This is dy. So far, so good. Are you guys getting the same thing? Are we all on the same page? Think so? A lot of this is just real calculation based problem. So there might be like a little arithmetic mistake, but I hope, yeah, I'm pretty sure it's all good. Just this is 6. Okay. Okay. So now that we get to that point, It's just integrating. And how do we integrate this? I do it pretty I do this pretty fast, job. I don't know. So I'm glad you tell me that I'm doing it fast. I feel like I'm doing it slow. I feel like I speak slow. I don't know. But then people say, "Oh yeah, you write too fast." I'm like, "Do I really write that fast?" I I don't notice that I write fast. But that's why I kind of pause. Is that supposed to be y squared over 2? What's supposed to be y squared over 2?
The second, when you're plugging in from negative y to y, um, you have negative parentheses negative y squared minus y squared over 2. Um,
Yeah,
if you're plugging in a negative y
yeah.
to it, and then you have the negative in front of it, wouldn't that become positive?
Well, you have to be very careful. Negative y, I'm placing it inside where x is, right? X is being squared. So negative y parentheses is being squared. So this is just an issue of so this is negative x over 2 squared, right? But I'm doing this. I'm doing negative y squared over 2. So the negative y is being squared. So negative y is positive y squared. But then there's that negative in front. So it's going to stay negative.
But then why didn't the other one become positive? The first
Which
y
one?
squared in the parentheses.
This one?
Yeah.
Well,
Oh, because
because,
it's x y.
yeah.
Okay,
And all
I
we're
got
doing is replacing the x with the negative y. So it becomes negative y squared.
okay, thanks.
Mhm. So then how do we integrate this part here? We use by parts, right? So u is equal to y squared. U prime is equal to 2y. V prime is equal to e to negative y. And v is equal to negative e negative y. So then you get what? So this integral is negative y squared e to negative y evaluated from 0 to infinity plus 2 integral y e to negative y from 0 to infinity. This will be equal to what? 0 for many reasons when you plug in the infinity, right? When this approaches infinity, this whole thing becomes 0 quicker than this becomes infinity. So it goes to 0. And then if you plug in 0, of course, you get everything equal to 0. And and then if you notice, again, we can do the integration by parts again, but then what is this? Isn't this the expected value of y when y is an exponential variable, random variable, right? Where lambda is equal to 1. So what's the expected value of a random variable where lambda is equal to 1? Isn't it just 1? We're going to get 1 for this. So then this integral here is really just equal to 2. It equals 2. Why does it equal 2? Well, if this equals 1 times 2 plus 0, this is 2. So this here is 4c equals 1. So what does c equal? 1 over 4. We're good? Any questions? Great. So then part C, right? We want to do part C. So part C, what does it ask for? Part C asks for a density function of y. The density function of y. That's right. Okay. So we have f of y goes from what? Negative infinity to infinity of f of x y, but you're doing it with respect to x. So all the x's, but what are the x's ranging from? What's the x's ranging from? X is in between what y and negative y would be. So the bounds here have to be exactly what you think it's going to be. Negative y to y of what? This is 1/4 y minus x e to negative y dx. So you can factor out the 1/4 e to negative y and just integrate from negative y to y of y minus x dx. And this here is the same thing we did here already, right? We already did this integral. We did this integral already. And what did you get? 2y squared? Isn't that right? Isn't this already 2y squared? So this will equal 1/4 times e to negative y times 2y squared, which equals 1/2 e to negative y squared. This is f of y, the marginal density. And y goes from 0 to infinity.
Okay, I think I keep mixing up which bounds to set because, okay, so we're integrating in respect to x, but we're solving for y, I guess. But because we're integrating in respect to x, we have to take the x bounds, which was negative y and y. But
Yeah.
then when we write the marginal density, we still refer to the y bounds in the final answer because that's what y is ranging from.
Yes.
Okay, got it. Thank you.
Mm-hmm. Okay. With sum of independent random variables. So I don't think we have a problem like that, Sering, on the review sheet. So like I can give you the whole kitchen sink if you want, but I've chosen problems here that I think should be on the final. So I don't think we have a problem because we haven't done too much about that. We haven't done too many problems with sum of independent random variables. Yeah, I don't think we did yeah, that one was it was quite kind of just in passing that I went over it. I don't think I even gave you homework on that problem, on that kind of problem. So in essence, don't worry about sums of independent random variables for the final. Hijab, of course. The final is cumulative. So which means it could be anything from everything you've done. I just told you one thing that's not going to be on it. But everything else that you've seen already in review sheet 2, review sheet 1, right, is fair game because you've done it already, right? So again, this is cumulative. This is pretty standard in a lot of exams. Okay, so 2.1, A and C. All right. Okay, so here we have 2.1, number 1, A and C. Let me just make sure that this is indeed. Okay, so we have a joint probability mass function. Great. This is compute a conditional mass function of x given that y equals I. So I want to know part A. I want to know the probability that x equals 1, for example, when y equals 1. So what does that look like? The probability that x equals 1, given that y equals 1. Pardon me, the probability of x, right? When y equals 1. So when y equals 1, we're only really looking at this. When y equals 1. So then what's the probability of x when y equals 1? Well, what's the probability that x equals 1 when given y equals 1? It's kind of redundant a bit, right? We're saying this. When y equals 1, the probability of x equals 1 is an eighth. And then when x equals 2, when y equals 1, it's also an eighth. And then so this is when y equals 1. Now what if when x equals 2, when y equals 2? So then you get the probability that x equals 1 given y equals 2. Let me just see. Hold on. Oh, wait, it's not that straightforward. Pardon me. No, this 1/8 is the probability that x and so okay. So before we do that, hold on 1 second. I was getting ahead of myself. When you want to compute this, right? Remember, recall the probability when a given b. What does this equal? The probability of a and b over the probability of b. Okay. So if I want to find the probability that x given 1, given that y equals 1, I need to find a probability that x equals 1 and that y equals 1, but then divide that by the probability that y equals 1. And this would be the probability that x equals 2, given that y equals 1, over the probability that y equals 1. So it's not that straightforward. The numerator will be an eighth here, and this will be also an eighth. So it's going to be the same. But the real question is, what's the probability that y equals 1? So really what for part A, you have to find what's called the marginal density function. What's the marginal density function of y? Or I should say, what's the probability mass function of y? Only. Do you know how to compute that? So I thought you said that. I thought you said it, Alexandra. 1/8 plus 1/8. Do you know why it's 1/8 plus 1/8, which is a fourth? Yeah, you add up. So this thing here is exactly the probability when y equals 1. Why is that? Because we're adding all the x values when y equals 1. So this is a fourth. So then obviously here, this would be a half, right? So the probability that x is 1 given that y equals 1 is a half. And the same thing will go for the probability of x equals 2 given y equals 1. It's also going to be a half. Does that make sense? And then the same thing goes for this other conditional probability. This is the probability that x equals 1, y equals 2, given that the probability that y equals 2. And then this is the probability that x equals 2, given that y equals 2. Probability that x equals 2, comma, y equals 2. Or the probability that y equals 2. So what's the probability mass function that y equals 2? Well, add up all the different values for x, and then you'll get the probability of y equals 2. So what's a fourth plus a half? 3/4, right? So then you would get what? You get 1/4 divided by 3/4, and then you would get 1/2 divided by 3/4. Oh, yeah, don't let the word function throw you off. I know the terminology, I would say, in this realm of probability is not the greatest. The reason why is because you have several different elements that we're dealing with. We're dealing with discrete versus continuous. So the word probability mass function is equivalent to the probability density function. And why is it that the word changes, but we're dealing with the same idea? I'm not, so that's just semantics at that point. But the difference is that one is discrete, the other one is continuous. So it doesn't make sense to use the word mass in the way that they use mass for discrete. So that's why we use the word mass for discrete random variables. And yeah, and then density is the continuous version of the mass function. But then you have distribution function, which is different, and that can get confusing. It can. Probability distribution function is not the same as a probability mass function, which is not the same as a probability density function, which is, yeah, I get it. But the reason why it shouldn't be a problem is because you are computing the probability mass function. I know what you think as a function, you're thinking, oh, it has to be an expression in terms of x or in terms of y, right? But that's not the only way to express a function. Is that maybe you're accustomed to that. You're accustomed to saying, oh, this is a function. F of x equals 3x plus 2. So that's your worldview. I don't want to make it like that. Your perspective of what a function is. But a function can also be, for example, a set of ordered pairs. So you can treat this as this is also a function. Why? Because you have an input and you have an associated output. So for discrete random variables and talking about the probability mass functions of discrete random variables, there is no formula that we're looking for. We're just looking for the connection between, if I have an input, what would be the associated output? And that would constitute as defining the probability mass function. So I define the probability mass function as y equals 1 or y equals 2. And then I want to know what the variable is, or what the expression is, what the output is. So when y equals 1, the probability is 1/4. When y equals 2, the probability is 3/4. And that's it. And that would be my probability mass function. I just defined it. Yeah. the thing is, Alexandra, what the funny thing is, I also teach younger younger students from like middle school and high school, um, apart from Queens College. So then, literally yesterday, I was talking about what a function was, and they they did not know what a function was. And it's not just that they don't know. A lot of students, they hear the word function and then just, oh, it's f of x, and then but they don't even know how to explain beyond that. They don't know what the the overlying the general idea what a function is, which is very essential, right? Because you see what a function appears in many different domains, fields, particularly, right? When you program, you talk about building functions. That idea of function is still the same as what mathematically we're speaking of. Of course, we get to a different world with functions, right? We're talking about domain range and all that. But the idea of input and output is essential in any aspect of what functions may appear as. And that's something that students don't keep in mind. And that's the way it goes sometimes. So I try to help my best, do my best to try to make sure I fill in the gaps, because I remember at one point in time, I myself had no idea what a function was. I didn't know. People talk about functions. I'm like, wait, what are you guys talking about? What's a function? What's so special about functions? Well, it's very essential. But anyway, so 1/4 divided by 3/4 is a third. 1/2 divided by 3/4, it's 2/3. And so I found the conditional mass function. I found it. It is here. So let me just summarize. So the probability when x is 1, given y is 1, is a half. Thank you, Mir. I appreciate that question. Wait, I don't know if that was facetious or if you really want to know. So y equals 1 is a half, right? And then this is x equals 1 given y equals 2. And then the probability that x equals 2 given y equals 2. So I've calculated the conditional mass function. So this is it. This is the conditional mass function of x given y equals I for I equaling 1 and 2. This is when I equals 1 and this is when I equals 2. Or in other words, yeah, this is when y equals 1 and this is when y equals 2. Okay. And then once we have that, then part C, I don't think it should be too bad, right? When x y is less than or equal to 3, for example, when is x y less than or equal to 3? Well, what are the only combinations of x and y? You have only 4 of them, right? So if you see this, right, what they're asking you is when is x and y less than or equal to 3 for the x's and y's that we have. We have x equals 1 or 2 and y equals 1 or 2. So you can treat this as, oh well, I can have the probability that xy equals 1, right? Or I can have xy equaling 2, or I can have xy equaling 3. That's what this means. That's what this means, doesn't it? But each of these events are what? Mutually exclusive. You can't have a product of two numbers equaling 1 while at the same time equaling 2 and at the same time equaling 3. So they're mutually exclusive. What does that mean? I can add them. The probability that xy equals 1 plus the probability that xy equals 2 plus the probability that xy equals 3. And of course, I could do xy equals 0. But the thing is, there is no numbers here, 1 and 2, that multiply to 0. So I'm not even considering that. And if you want to see, there is no two numbers, combinations of 1 and 2, that when you multiply give you 3. So the probability of this happening also is 0. So I only have these two here. The probability that xy equals 1. Well, if xy equals 1, that means that x must equal 1, y must equal 1. What's the probability that x equals 1 and y equals 1? It's an eighth. Do you guys see how I'm doing that? It's an eighth. And then what's the probability that xy equals 2? Well, x could equal 1, y could equal 2, or x could equal 2, y equals 1. So I have two instances. And these two instances are here. 1, 2, which is a fourth, and 1/8, which is 2, 1, which is an eighth. So in this, I have a sum of 1/8 plus a fourth. And that's how I calculated it. So 1/8 plus an eighth is a fourth, plus a fourth is 2/4, which is a half. Make sense? And that's how we hack away at these problems. So like the probability, right? When x plus y is greater than 2. So then what two numbers are greater than 2? Yeah. xy less than 3. The 3 refers to the input. It's the product of the inputs. It's the product of the endpoints. No, the 3 has nothing to do with, remember, probability can't be bigger than 1. So this is a pretty simple problem, but it's kind of, it's, and at the same time, it's profound, it's deep, because once you start understanding what this stuff is inside here, right? It's unlike the functions that you're accustomed to. You don't get inputs that look like this, right? Your functions are very nice, straightforward. They're like, oh, you plug in a number and you do stuff to it, right? You plug in numbers. In probability, you're not plugging in numbers per se. You're plugging in events. This is an event. Now, this event is dependent upon what x and y can be. And x and y has only a finite number of instances. X could be 1 or 2, y could be 1 or 2, and that's it. So then you're basically saying you're checking what values of x and y when I perform this product, right, gives me something less than or equal to 3. Well, there's only 3 instances. And what the probability mass function of x and y, that joint probability, what it tells you is the probability of those instances occurring. P11 is saying the probability that x equals 1 while y equals 1 at the same time is an eighth. And the probability that x equals 1 while y equals 2 is a fourth, and so on. So then that's the information that we're utilizing here. Okay, and this stuff, as you can tell, this stuff inside here can be so many different, like you can just make up an inequality with x and y's. In this one, we had a product. In this one here, we have a sum. So we're saying, hey, when is x plus y bigger than 2? Well, x and y can only have two instances each, right? So when is a sum of two different variables that only have 1 and 2 assigned to them bigger than 2? Well, x could be what? 1, y could equal 2, x could be 2, y could equal 1, or x could be 2 and y could equal 2, and that's it. Those are the only 3 instances. So then this is the same thing as saying the probability that x equals 1, y equals 2, plus the probability that x equals 2, y equals 1, plus the probability that x equals 2, y equals 2. And then we're just adding the probabilities up. So the only one that we're excluding is 1/8. So 1/8 plus a fourth So 1/8 plus, sorry, this is 1/4. 1/4 plus an eighth plus a half. And of course, when you add this up, it should be something less than 1/8 less than 1, right? So if you multiply this to 4, multiply this is a 2. So 2 plus 1 plus 4 is 7. 7/8. Okay, and the last one, the probability that x over y is greater than 1. Well, that can only happen when x equals 2 and y equals 1, or when that's it. There's no other way, right? So this is equivalent to saying the probability that x equals 2, y equals 1, or in other words, what's p2 of 1? You see, there's so many. I think this is the reason why probability can be a little bit confusing, is because there's so many different ways to express the same thing. What I'm saying is this is the same as this, which is the same as this. So p2 1 was what? 1/8, and that's it. There's not much else to this. Any last minute advice? Great question. Well, on what exactly? In life or what? Give away a tip. Start praying, right?